Welcome back everyone. Welcome back to this particular lecture of Unit 3. Today we will discuss Pmsm motor and Bldc motor. So let's start. So this first we will see the Pmsm motor. Pmsm stands for Permanent Magnet Synchronous Motor. And this is a type of AC synchronous motor that converts the electrical energy to the mechanical energy. And this in this PMSM motor, we use the permanent magnet in the rotor, and usage of this permanent magnet in the rotor, it increases the efficiency. Next, first we will see the construction of the PMSM motor. So in this PMSM motor, like any other DC machine, we have the outer frame. This outer frame, it is made up of the cast iron. So the main function of this outer frame is to protect the inner part from the damage. Basically, it acts as a protecting shield. Next, we have the stator. You can see the stator core is shown here. Next, we have the stator. So this stator core, it is made up of the laminated silicon steel. Previously also we have used the same material for the stator core because this material is having the high permeability. If a magnetic material is having high permeability, means it allows large number of magnetic lines of forces or magnetic fields to pass through it very easily. And what is this lamination in this laminated silicon steel? This lamination is the arrangement of thin sheets that combine together in order to reduce the hysteresis losses. So what is this hysteresis loss? Previously also we have discussed, when a magnetic material is getting magnetized or demagnetized repeatedly, the electrical energy loss as heat during this process will be very less if the hysteresis loss is less. So if we want to reduce this hysteresis loss, we need to use the laminated silicon steel. So this lamination is the arrangement of the thin silicon sheets and they are combined together. Okay. Then this gray color portion is my stator core, right? So at this inner portion of the stator core, we have some slots present here. Here, as per this diagram, we have 4 slots present. Okay. Now, in these stator poles, we have the stator windings. You can see this red color. These are the stator windings. Okay. Next, inside we have the rotating part or the rotor. The rotor of the PMSM motor, it is made up of the permanent magnet. That means it has the constant pole. Okay. And this is the rotating part of the PMSM motor. Next, we don't have any windings in the rotor because we already have the permanent motor acting as the permanent magnet acting as the rotor. Previously we have seen in the armature or the rotating part, we are giving the armature winding. In the armature slots we are having the armature winding, but since we are using the permanent magnet as the rotor, so we are not using any winding in the rotor. And also in this motor we are not using any commutator and the brushes because we are not having any winding in the rotor. So commutator and brushes are not required. Okay. Commutator is required for what? Commutator, it either converts the AC to DC or DC to AC, and brush is basically connects the rotating part of the DC machine to the stationary part. So since here we don't have any winding in the rotor, so we don't need to use any commutator or brush. Okay, so this is the big advantage of the PMSM motor. Number of components are getting reduced, And the magnetic material that we are, the permanent magnet that we are using, this magnetic material, it should be having very high coercive force. What is coercive force? It is a measure of the ability of a magnetic material to withstand an external magnetic field without becoming demagnetized. It indicates how resistant a material is to losing its magnetization when an external magnetic field is removed. This property is important in applications where permanent magnets are used, as a higher coercive force means the magnet will retain its magnetization better over time. I hope it's clear here. Next, so far we have seen the construction of the PMSM motor. Next, if we proceed towards the working principle of the PMSM motor, how it works, we have seen in the stator core we have the slots, and in slots we are having the stator winding. Okay, first we will give the three-phase AC supply to the stator winding. Okay, so these three-phase AC supply we are giving to the stator winding. This stator winding, it is a three-phase winding, we have seen, right? Either it is a star connection or it can be a delta connection, and we are giving a three-phase AC supply to this stator winding. Okay, as a result, what will happen? This stator winding, they will get magnetized, and a rotating magnetic field will get, you can see here a red circular portion is shown here. A rotating magnetic field will get produced in the air gap between the stator winding and the rotor, because we have given the three-phase AC supply to the stator winding. As a result, a rotating magnetic field is produced in the air gap. Okay, and this rotating magnetic field, it rotates at synchronous speed. Synchronous speed with what? Synchronous speed with the applied frequency of the AC supply. So the synchronous speed of these rotating magnetic field can be represented as Ns equals to 120 F by P. This F is the frequency and P is the number of poles. Okay, as well as we rotate number of poles of the rotor. Okay, now as well as we rotate the rotor from the external control to achieve the Ns speed. Okay, that means sometimes it is not always possible that the rotor can achieve the synchronous speed to the applied AC frequency. So in those cases we might need to give some external control, and in that case the rotor can easily be reaching to the synchronous speed over time. Now, when the rotor speed, if we define it as Nr, it is a rotating magnetic field of the stator. Why the rotating magnetic field of the stator? We have already discussed about this term in the three-phase induction motor. Because in the stator winding, we are giving the three-phase AC supply. As a result, a rotating magnetic field is getting induced in the stator winding. So, when this rotor speed is equal to the rotating magnetic field of the stator, what happens? The interlocking takes place. Okay, that means this south pole of the stator winding will get attracted to the north pole. Here the north pole of the stator winding is getting attracted to the south pole of the rotor. Here you can see this south pole is getting attracted to the north pole. Here this south pole is getting attracted to the north pole, and this is happening for a particular instant of time when the rotor is positioned like this, because stator is stationary, right? So for a particular instant when the rotor is positioned like this, so interlocking between the opposite polarity takes place between the rotor and the stator. Okay, so in this condition, what happens once the rotor starts rotating at the synchronous speed, then previously the external control that we were applying to achieve that synchronous speed, this external control can be removed. And that means we use the external mean in this PMSM motor to achieve the synchronous speed. So this kind of PMSM motor, it is not a self-starting motor, unlike the three-phase induction motor. Okay. Next, if we look at the applications and the advantages and disadvantages, this PMSM motor, it is used in air conditioning system, it is used in refrigerator system, it is used in AC compressors, it is used in washing machines, it is used in automotive electrical power steering. What are the advantages of this PMSM motor? It provides higher efficiency at high speed. It is available in different sizes, and installation and maintenance is easy compared to induction synchronous motor or three-phase induction motor. But the disadvantage of this PMSM motor is it is very expensive, and PMSM motor, it is not a self-starting motor. We need to give some external control in order to achieve the synchronous speed. Moving on, next topic is BLDC motor. Okay, so what are the so many motors we are just learning one by one. So we need to understand the construction and working principle of each and every motor. What is the advantage, disadvantage of a particular motor, how to overcome them, those disadvantages. Then only we can learn it better. So next topic is BLDC motor. So we have previously discussed DC motor. So in DC motor, there are some disadvantages. In the stator field winding, when we are energizing the stator field winding by giving the DC supply, so as a result there will be some loss. I square F R loss. I F, that current is a field current. Okay, so there are some losses getting induced in the stator field winding. Then there will also be commutation brush losses due to the sparking caused by the induced voltage in the armature winding. Okay, in the armature winding, whenever the EMF is getting induced, because the armature is kept inside the magnetic field of the stator, so whenever the EMF is getting induced in the armature winding, it will cause some sparking, and it will ultimately lead to the commutation brush loss. Okay, now first of all, let me tell you one thing. In this BLDC motor, we are not using any brush and the commutator. Brush and commutator both are removed from the DC motor. In that case, we call it as brushless DC motor or BLDC motor. So if we want to design a motor without brush and commutator, then first we need to understand why we need the commutator and the brush in the first place. Okay, so this is the commutator. This is the commutator. We have previously seen this commutator is nothing but a split ring. It is a metallic split ring. This is a metal, this is a metal, so in between we have a air gap, and with this commutator we have these brushes, carbon or graphite brushes. They are touched to the commutator, not connected, but they are touching the commutator. Okay, so what is the main function of the commutator? This commutator, it converts the AC to the DC. Okay, in case of a generator, if we have a DC generator, then the commutator, it will convert the AC to the DC. Okay, but if we have a motoring action, in case of a DC motor, this commutator converts DC to AC. Okay, so in case of a DC motor, we get DC at the supply side, and in case of a DC generator, we get the DC at the terminal side. And AC, where we get? AC we always get in the armature winding of the rotor. Okay, that means the commutator, in case of a DC generator, it acts as a mechanical rectifier because it converts the AC to DC, and in case of a DC motor, this commutator, it works as a mechanical inverter. Now if you notice, I am using a term mechanical rectifier, inverter. Why this mechanical term I am using? Because this DC machine will work only when the machine is rotating. Some mechanical action is taking place, otherwise this commutator is useless. Whenever the rotor is rotating, whenever the machine is rotating, then only this commutation action will take place. Okay, that is why we are using this mechanical term. Okay, now what is the need of the brushes? So this is the need of the commutator. Now what is the need of the brushes? This brush, it basically connects the rotatory armature winding with the stationary supply. Suppose you have a stationary supply with some DC battery. With this DC battery, you are connecting the rotor. Okay, this rotor of the motor. So this is the use of the brush. This brush will connect the rotating part or the rotor to a stationary DC supply. Okay, this connection is the brush connection. Okay, this brush will connect the rotating armature. This is the rotating armature to the stationary supply. Okay, next, now we told that in the armature winding always AC will get induced, but here we are discussing the DC motor. So why we need the AC in DC machines? What is the requirement of this AC induction in the DC machine? Okay, so the EMF that is getting induced in the armature winding, it can be either getting induced in the dynamic way or static way. Dynamic way means the armature winding or armature conductor, when it is placed in the stationary magnetic field of the stator, and when the EMF is getting induced in the armature conductor or armature winding, it will start cutting the magnetic flux of the stator. Okay, so in this way also EMF can get induced in the armature winding, or it can also get induced by the variable flux. Variable flux means in the stator field winding we are giving the DC supply to energize them. If we change the DC supply, then that magnetic field will also change in the stator, and the magnetic field linking to the rotor armature winding, it will also changed. Okay, so in either way the EMF can get induced in the armature winding. Okay, now in DC machine, in the armature winding we need to give AC, and in the field winding we are giving the DC. Okay, now armature winding means, suppose in our house, outside of the house, if there is some DC generator, the two terminals of the DC generator is the armature winding. Okay, now suppose a DC motor is connected to some battery. Okay, so the two terminals of the DC motor that is connected to the battery, it is called the armature winding. Alright, now in DC motor what we do? In DC motor we have the stator, which is the stationary part of the DC motor. In the stator, what we do? In the stator we have the field windings, and we give the DC supply in order to energize the field winding. So let's say this is my stator poles. Okay, we are energizing these stator poles by giving them the DC. Okay, now inside what we have the rotor. Okay, in the rotor we have the armature winding, and in the armature winding we are giving the AC. So how we are generating the AC in the armature winding? Suppose if you have a battery, from the battery you are getting the DC. Now through this mechanical commutator and the brush, this DC will be converted to the AC, and this AC is given to the armature winding of the rotor. Okay, so this commutator, what it does, mechanical commutator, why we are calling it mechanical, just now I have told, because when this rotor is rotating, then only this commutator will be able to convert this DC to the AC. That is why it is called mechanical commutator. Okay, now what is this brush? This brush is connecting the rotating part of the DC motor to the stationary part. Okay, now doesn't matter. So here what we are observing, in DC motor we are keeping the armature in the rotor. Okay, and doesn't matter armature wherever you keep in the world, whether you keep it in the stator, whether you keep it in the rotor, AC voltage will always get induced in the armature winding. Okay, but in DC motor we are keeping this armature winding in the rotor, and AC voltage is getting induced in the armature winding using this mechanical commutator. Okay, now this is what happens in the DC motor, but we are going to design the BLDC motor, and we have aimed to design this BLDC motor by removing the commutator and the brush. So let us see how we can design this BLDC motor by removing this mechanical commutator and the brush. So in the BLDC motor, what is happening, you can see this is my rotor. This is my rotor and this is my stator. So in BLDC motor, two changes we are doing. That means we are keeping this armature winding at the stator, and obviously this in the armature winding AC voltage will get induced, but we don't know initially how the AC voltage will get induced in the armature winding. What we are doing is we are keeping this armature winding in the stator, and in the rotor we are giving the field winding. Okay, but inside the rotor, instead of the field winding, we are replacing with the permanent magnet. Okay, so when we are using this permanent magnet, that means we are all, and when we are giving this DC to the rotor, so constant polarity poles are getting generated. We are making these two changes. First change is we are putting this armature winding in the stator, and inside the rotor, instead of field winding we are using the permanent magnet. That means we are already getting the constant field poles in the rotor. Okay, now how to generate the AC in the armature winding of the stator? Okay, let us see. You have a battery. From the battery we are having the DC supply. Now in the DC, from this DC supply we are using an electronic commutator instead of a mechanical commutator. This electronic commutator, it is a static commutator. It will convert this DC supply voltage to the AC voltage, and it will give it to the armature winding of the stator, and this is how the ACMF it is getting induced in the armature winding. Previously we didn't have this electronic commutator, But now as the power electronic is getting progressed, we have this electronic commutator or the static commutator, because see, the rotor is already rotating. Okay, we have this permanent magnet in the rotor is already rotating. We don't need to connect this rotor to any stationary part. That is why we don't need any brush here. Okay, because what is the requirement of brush connects the rotating part of the motor to the stationary part, but rotor is already rotating. The part that is already rotating, we don't need to give anything to it, so we don't need to connect this rotating part to the stationary part. That is why we don't need any brushes here. Okay, but we need the electronic commutator. This is the static commutator which only converts this DC to the AC. Unlike the previous case, previously in DC motor, conventional DC motor, we are using the mechanical commutator. That means when this rotor is rotating, then only this commutator action will take place. That means then only this commutator will convert this DC to the AC. Okay, but now since the power electronics has progressed enormously, we don't need to use brushes anymore. We don't need to use the mechanical commutator anymore. Electronic commutator is enough. So this is how the BLDC motor is constructed.